Welcome to the deep dive. Today we are jumping into the world of science fiction, but while we're bringing our physics textbook along for the ride,
That's right.
we're tackling that big question: how fast could a human really run? And maybe more importantly, what happens when physics kicks in if you try to go faster? Like way faster.
And our inspiration, drawn from the sources you sent us, is none other than DC's Flash. I mean, this is a character credited with speeds that are just mind-boggling.
Yeah, what kind of speeds are we talking about?
Well, sometimes it's only 2,500 miles per hour, which, is already faster than most fighter jets.
Okay, already impressive.
But then it ramps up to needing to move faster than light itself, 186,000 miles per second often, just so he can, fiddle with time.
Right, the classic time travel trope. But the sources, they paint a pretty grim picture if a real person tried that, don't they?
Oh, absolutely. Forget turning back time. For a normal human, even a tiny fraction of that speed, you're looking at, instant catastrophe, melting faces, shattered bones. It's not pretty.
Okay, so that sets up our mission for this deep dive. Two parts, really. First, what's the actual hard biological limit for human speed? The absolute ceiling.
And then, second part, we throw biology out the window for a minute.
Right.
We assume a speedster can exist. Let's use the CW's Barry Allen as our model, 183 centimeters, 88 kilos. And we ask, what does physics demand? What's the cost?
Okay, sounds like a plan, but before we get to melting faces, let's ground ourselves. The fastest human we've ever seen. That's got to be Usain Bolt.
Bolter benchmark, definitely. His 2009 world record for the 100 meters is 9.58 seconds. Still standing.
And during that sprint, what was his top speed?
He hit about 27 miles per hour. That's 43 kilometers an hour. Fast for a human, but not exactly breaking the sound barrier.
And remarkably, that record's over a decade old now. No one's beaten it.
Which leads into a really interesting, maybe slightly controversial argument from the sources.
Yeah.
This comes from Mark Denny, a biology professor at Stanford, works in biomechanics. He argues that Bolt's record, it might never be significantly beaten.
Never. That sounds pessimistic. What's his reasoning?
Well, Denny did this huge analysis looking at race data going way back to the 1920s. Not just humans, but also greyhounds and thoroughbred horses.
Okay.
And what he found across the board was that performance improvements, they were clearly plateauing. Like the big, easy gains were long gone. We're hitting a ceiling.
I can see why that's disappointing. You think about advances in training, nutrition, tech. Surely we can keep shaving off milliseconds, right? We can't be at the absolute limit already.
Denny suggests we're pretty much there, at least for humans as we are now. He uses the Horse Example Secretariat in 1973, basically set the peak for horses.
Wow, 1973.
Yeah. And attempts since then to breed even faster horses often just result in the animals breaking down. Their bodies literally can't cope with the forces involved. The biological hardware has limits.
Okay, so based on all that data, what did Denny actually predict? The hard number for the human 100-meter limit.
His calculation landed on 9.48 seconds.
9.48. That's only a tenth of a second faster than Bolt's current record.
Exactly, just 0.1 seconds. And he mentioned, when the paper came out, people felt a real sense of disappointment. We don't like the idea that future Olympic records might just stop falling.
Yeah, it goes against that whole faster, higher, stronger ideal. So, okay, let's get into the why. Why 9.48? If you imagine a perfectly built runner, say taller than Bolt, maybe 218 centimeters, perfectly proportioned, why are they still stuck?
Fundamentally, it's our design. We're bipeds. We're built more for endurance, think marathon running, not the explosive short bursts of speed you see in, say, a cheetah. They have that super flexible spine, long legs relative to body size.
Yeah.
They're built differently.
But the real limiter is deeper, right? Inside the muscles themselves.
That's the core of it. The ultimate speed limit comes down to how fast your muscle fibers can physically contract, and that speed is set by the turnover rate of two key proteins, actin and myosin.
The little molecular ratchet.
Pretty much. They work like tiny oars, pulling things along. You can train to make them more efficient, stronger, but there's a fundamental chemical speed limit to how fast they can cycle. You can't make them ratchet infinitely fast.
And even if you could, you'd hit another wall, the mechanical one.
Right. Your skeleton, your tendons, your bones. They can only handle so much force before they, break.
And here's the catch you mentioned earlier. If you tried to make bones stronger, more robust to handle more force,
They get heavier.
Right.
And that added weight makes you slower. So you're kind of stuck in this physical trade-off. You can't just beef up the structure without paying a penalty somewhere else.
It feels like a biological dead end. But the sources did offer a glimmer of hope. They called it the cheat code.
Yeah, the cheat
Yeah.
code. Basically, if you want to smash that 9.48-second barrier, you can't do it with biology as it currently exists. You need genetic engineering.
So redesigning humans.
Essentially. You'd have to aim for things like fundamentally longer legs, maybe tweaking where muscles attach to bones for better leverage, or even designing completely new muscle fiber types that bypass that actin-myosin speed limit.
Wow. Okay.
But until someone figures that out, 9.48 seconds looks like the peak for Homo sapiens running on two legs.
Okay, fantastic explanation. Let's file that under human limits now. Let's forget all that sensible biology.
Let the fun begin.
Exactly. Let's enter the danger zone. Assume Barry Allen, our 88-kilogram speedster, somehow can exist. What does physics have to say about his lifestyle?
Well, physics has a lot to say, and most of it isn't good news for Barry. Let's start small, relatively speaking. Running on water.
Okay, a classic Flash move.
But pull that off. Just skimming the surface without sinking. He needs to hit roughly 30 meters per second.
Which is fast, but maybe not super speed in his world.
Right. It's quick, but we're aiming higher.
Yeah.
The sources looked at a much crazier stunt. Imagine the Flash having to check an entire city block, running up buildings, down buildings, checking every single room, all in just 3 seconds.
3 seconds. The speed needed for that must be astronomical.
The calculation, based on a real Toronto district layout, came out at 30,967.67 kilometers per hour.
Wait, say that again?
30,967.7 kilometers per hour.
Okay. Just to help you, the listener, wrap your head around that. That's nearly 80% of Earth's escape velocity. And it's more than 25 times the speed of sound, Mach 25.
Yeah. And when you're moving that fast through air, physics starts demanding a heavy toll. The first major problem. The air itself becomes an obstacle.
Air resistance, right. Drag.
Exactly. But it's not just simple drag. The force of air resistance increases exponentially with your speed.
Ah, so double the speed isn't double the resistance, it's way more.
Way, way more. To maintain Mach 25, the Flash has to constantly exert this exponentially growing force just to counteract the air pushing back against him. The energy required starts going vertical almost immediately.
And that friction with the air, it doesn't just slow you down, it heats things up. A lot.
Think about meteors. They glow white-hot and burn up, entering our atmosphere purely from air friction.
Okay.
The sources bluntly state that Barry's body, and especially his suit, often shown as latex, spandex, would need to be, and I quote, very resistant to sweltering heat.
Sweltering heat sounds like an understatement.
It really is.
Yeah.
Forget scorching. We're talking about instantaneous melting, probably vaporization. His suit wouldn't just catch fire, it would likely cease to exist.
Oof. Okay, so that's the external problem. What about inside his body, getting up to that speed, accelerating that fast?
Yeah.
Humans aren't solid objects.
Precisely. We're mostly water. And there's a hard limit to how much acceleration the human body can take before it stops being an intact body.
What happens?
Inertia takes over. If Barry accelerates too quickly, his brain would effectively be smashed into the skull.
Grim.
And all his internal fluids, blood, lymph, spinal fluid, would surge violently to the back, compressing organs. The body's structure just can't handle those G-forces.
You know, it's funny, the sources actually mention a moment from the X-Men movies that touches on this.
Oh, yeah.
Days of Future Past. There's that scene where Quicksilver is moving Magneto at super speed, and he literally has to cup his hand behind Magneto's head to stop his neck from snapping backward from the acceleration.
Huh. That's actually surprisingly good physics for a superhero movie. It acknowledges that inertia is a real killer.
But hey, let's imagine he can survive the acceleration and the heat. There's actually a positive side effect from the physics, right?
There is. If he can generate the immense force needed for that kind of acceleration, it means he's also incredibly strong. The sources suggest he actually be the strongest superhero of them all, in a way.
How so?
Because force equals mass times acceleration. To get his mass moving that fast requires enormous force. So a punch thrown at even a fraction of his top speed, it would carry insane momentum and deliver a devastating, likely lethal impact force.
Small consolation when you're about to burst into flames, but okay, strength is good. But this brings us to maybe the most fundamentally broken aspect of it all. The energy, the fuel required, the caloric crisis.
Yes, the big one.
Let's go back to that city block search. Mach 25 for 3 seconds. What's the energy cost?
Okay, so first baseline. An active adult male needs, maybe 2,300 calories a day just to live, move around, basic bodily functions.
Got it. 2,300 calories for a normal day.
Now add the cost of that 3-second Mach 25 sprint based on scaling up from like an elite marathon runner's energy burn rate.
Okay.
The Flash would need to burn an extra 128,100,557 calories.
100. Just say the number again.
128,100,557 calories.
For 3 seconds of work.
On top of the 2,300 he needs just to not die.
My brain can't even process that number. Before we even talk about eating that much, where does an 88-kilogram human body even put that much energy? How do you store or metabolize 128 million calories almost instantly?
You don't. That's the whole point. It's biologically, physically impossible. There's no digestive system, no metabolic pathway in existence that could handle that kind of energy flux.
It's why the sources kept saying
Barry Allen is dead. Again, because every time he pulls off one of these stunts, he violates energy conservation on a scale that's just incompatible with life as we know it.
But just for fun, help us visualize 128 million calories. Translate that into, I don't know, fast food.
Okay, get ready for this. You need to eat 76,251 McDonald's chicken McNuggets.
76,000 McNuggets.
Or, if you prefer burgers, 185,653 double Big Macs.
Good Lord. Okay. The sheer absurdity is landing now.
It's an energy requirement so far beyond biological limits, it's firmly in the realm of magic or, the speed force.
What a journey. Okay, let's try to wrap this up. We started with biology. Humans have a likely speed limit around 9.48 seconds for the 100 meters. To go faster, you need genetic engineering.
Then we ignored biology. We let Barry run. And physics immediately hit back with exponential air resistance, friction generating enough heat to vaporize him, internal trauma from acceleration.
And finally, the killer blow. An impossible energy requirement. 128 million calories for a 3-second sprint. Barry Allen is indeed dead again.
But the sources raised one more crucial point, didn't they? Something beyond the physical body and the energy.
Right. Even if you solve all those problems, there's the brain.
You'd need a super brain.
Why is that the final piece of the puzzle?
Because what good is moving at Mach 25 if your brain can't process the world whizzing by? You need to perceive, react, and coordinate your movements at the same incredible speed.
Otherwise, you're just
a high-speed meat projectile. You'd run into things before your brain even registered they were there. Your reaction time has to scale with your movement speed. Your neurons need to fire impossibly fast.
Which brings us to a really interesting final thought for you, the listener, to chew on. Our sources suggest the human biological running limit is basically here. Going further needs genetic modification. But we live in an age obsessed with tech AI, cybernetics, enhancements.
Yeah, that's true.
So if our biological peak performance is more or less fixed, where should we focus our efforts to get faster? Do we keep trying to tweak the human body through genetics? Or do we accept biological limits and instead pour our energy into creating, well, non-biological ways to achieve speed? External enhancements, machines, something else entirely?
It's a fascinating question. Maybe the future of speed isn't about making humans run faster at all. Maybe it's about building something separate that runs for us.
A provocative thought to end on. Thank you for sending in these amazing sources. It's been incredible diving into the science behind the super heroics.
It really has.
Yeah.
Always fun to see where science fiction meets cold, hard reality.
We'll catch you on the next deep dive.